Hello, my name is Alejandro Salas, and this is a code walkthrough of my binary search tree project. So to start my program out, we have a structure of node called node, and in this structure we have the data that we want to insert into the node, and we have a node pointer pointing to the left and pointing to the right, because that's how we branch out in a binary search tree. So that's the initial data structure. And moving on to the next function, which is the new node function. And basically this function will run every time that we want to insert a new node into the tree. And what's going to happen in this function is that we're going to create a new node pointer and having it equal to a new node. And the data inside of this node is going to be passed through the parameter that we want to insert. So the keys, and as we can see in the main, the keys are basically just an array of unsorted integers. So these are the keys that we want to insert into our tree. So if we go back up top, we're going to insert the data, and then we're also going to, in this new node function, we're going to set equal the node pointer to the left and the node pointer to the right equal to null, because as they shouldn't be pointing to anything since they're a new node, and then we're going to return the node. Moving on to the next function, this recursive function is basically what it's going to do. It's if the root is not null, then it's going to go to the left side of the tree and print out that data, and then go back and then go to the right of the tree and print out that data. And this is going to display the data in order, because the way the binary search tree works is that the data stored on the left side of the tree is smaller than the root, and the data stored on the right is bigger. So with that philosophy, then we know that if we display it from the left to the right, then we know that data is going to be in order. Moving on to the next function, the maximum key. This is basically helping me to find the maximum value in the tree, and this will help me delete a node when we're trying to delete a node that has two child. And I'll explain more on that later, but this is basically traversing through the right of the tree and then returning that pointer when it's the last one, so the maximum one. The insert function. This recursive function is basically going to call itself every time we want to insert a new node into the tree. So if the root is null, then we're going to create a new node, and this is going to be true every time we call this function again, because once we create a new node, then we know that that root is going to be passed down to the current node, and that current, well, it's new, so it's null. So we're going to go back to this new node function and insert it with the parameter with the argument of key, and we're basically going to create a new node. So this happens, but this happens to the left if the data that we want to include is smaller than the root, and it happens to the right if the data that we want to include is bigger than the root. And then we return the root. So the deleting function. This function I had the most trouble with. I don't know if it's going to be a pattern with data structures, but I find to have the most trouble with deleting nodes in data structures. But either way, let's jump right into it because it's a roller coaster. We pass the root. Note that we pass the root through reference to the function, and so let's jump right into it. So the root is going to, if the root is equal to null, basically saying that the key that we want to delete is not found, then we're just going to return it because there's nothing to calculate or anything. So if the key that we want to delete is less than the root, then we're going to go on the left side of the tree, and if the key that we want to delete is bigger than the root, then we're going to go on the right side of the tree. So if if statements help us redirect the path in which we want to go, and then this else will run. Sorry about that, my microphone died. This else, as I was saying, this else will run once the key is found. And there are three cases that we need to take account on when deleting a node in a binary search tree. And the case number one is that the node that we want to delete has no children, so it's a leaf node. So this is basically saying that if the node that we want to delete does not have a left pointer and does not have a right pointer, then we just delete that root and then make that node equal to null. So I made some illustrations to help me understand these cases further. And so this is case number one. Say that we want to delete node 25. It has no children. So what we just do is we check if it's pointing to anything, left or right. It is not. And if it is not, then we just simply delete it. And this is what's happening in here, line number 82. So the second case, moving along, the second case happens if the node that we want to delete has two children. And this is the most complicated case in my opinion, and this is what it's checking. So if it does have a node pointing to the left and a node pointing to the right, what we're going to do is create this new node pointer called predecessor and find the next value in order in which of the node that we want to delete. And then we're going to make that data of the predecessor equal to we're going to set that predecessor equal to the data from the node that we want to delete, and then delete the predecessor. I know it sounds confusing, but with this illustration, I feel like it's going to make a little bit more sense. So case number two, say that the node that we want to delete has two children. So say that we want to delete node number 10. So what we're going to do is going to find the predecessor, which is 12, and we're going to set it equal to that node, and then we're going to delete the predecessor. And as we can see, this follows all the rules of the binary search tree, and it works. So it's perfect. The third case and the final case that we want to take account on is if the node that we want to delete has one child. So if the node that we want to delete has only one child, then it has only one pointing to the left or right. And then we're going to find that child node and set that value equal, again as with the other case, set that value equal to the one that we want to delete, and then basically delete that child. So if we go back to the illustration, we can see that if we want to delete number 20, then we're going to basically set the child equal to the root, and then we're going to delete this child. And this follows all the rules of the binary search tree, so it works perfectly. Going back, so this is the delete function. This takes in account all the three cases and functions perfectly. So going to my main function and the one that does it all. So in my main, we have a new node pointer null root equal to null because, well, it hasn't been assigned to anything, and we have the keys that we want to insert into the tree. And then we have inserting the keys. So for every key inside of keys, so for every time we're going to set root equal to insert, and this is basically going to let us go through the insert function and set each key to the tree. And then we're going to print out in order the tree, sorry, not the list. And then I have here illustrating how we delete a value from the tree. We're going to delete number 12. So we can see here that delete node from the root, we're going to delete 12, and then we're going to print out the tree once more. So if we run this program, we should have an ordered tree list, and we have 8, 10, 12, 15, 20, and 25, which is perfect. We're going to now delete number 12, and we can see that the number 12, the value, has been successfully deleted, and the list remains in order. So that's been my program from going over the binary search trees. I had a lot of fun doing this program, but also a lot of trouble with the deleting function. But at the end of the day, I've finally got it to work, and I'm happy with the result. So anyways, that's been my project. Thank you so much for your time and attention.